Good morning, dear students. Welcome to Purnachandra Higher Secondary School. Okay. So in this video lecture, we are discussing about circular motion. Okay, is an important part in the chapter of laws of motion. Okay. So let us discuss how a object is having a circular motion. Okay. So let us define it first. That means what is a circular motion? Now, an object which is, listen very carefully, the object which is moved in the circumference, along the circumference of a circle. The object, if the motion of the object along the circumference of the circle, then that type of motion is called circular motion. Clear, all of you? Again I will repeat, the motion of an object, if it is along the circumference of the circle, then that type of motion is called your circular motion. Okay, we can take an example. For example, the revolution of electrons around the nucleus is a circular motion. Similarly, the revolution of Earth around the Sun, okay, that is approximately a circular motion. Clear, all of you? Similarly, we can take a practical example that suppose with a string we are attaching a stone, okay, and we are revolving the string in that manner. Then that type of motion of the your stone with the string, that type of motion is called your circular motion. Clear, all of you? Okay. So these are the examples of your circular motion. Now, what happens actually? If suppose we are revolving a stone with the help of a string, and at a certain moment I will release it, then what happens? The stone along with the string will move in a straight line. That is a very important point. As look at this figure very carefully. Okay, that means if at any point, I have just shown here 4 points, but you can take any point in this circumference during this motion. At every point when the stone is released along with the string, it will move in a straight line with a velocity v. Clear? With a velocity v. That means we can say that the linear velocity during a circular motion, the linear velocity gives us a tangent at that point where the object will released. Clear? At this point it will also, the linear velocity also tangential in this direction. At this point the linear velocity tangential in this direction. Okay. At this point it also tangential. It is a tangent to this circular motion or to this circumference. That is it. Okay. The linear velocity is very important. Clear? Tangential to it. First point. Clear? And when the object is released or the stone is released, it will move in a straight line with a linear velocity v. Clear? Okay. So now this is the fundamental part. Now we will discuss what are the important factors or what are the important physical quantities relating to the circular motion. Okay. So suppose for this, let us look at this figure. So what I have taken here, suppose a object is present at P. All of you look at the figure. Suppose the object is present at P, okay, and the object is moving from P to Q in circular motion. Then let the path covered is del S, or you can tell the circumference, the part of the circumference covered by the object be del S. At this moment, the angle made at the center by the object, okay, what is the angle? What I will take? Not del theta. Suppose the angle made by this R, okay, so this is my radius, or you can tell it as a radius vector. I will count to you what is radius vector. But simply when the object is moving from P point to Q point, it will draw an angle of del theta at the center. Clear? So let us first discuss what is a radius vector or what is a position vector. Your radius position vector. Clear? So a radius vector So radius vector. Okay, so this vector, that is OP vector, is your radius vector. All of you can visualize that one. OP vector is your radius vector. So what is actually radius vector? Now the radius vector is the vector which gives the position of the object with respect to origin during a circular motion. Okay, that means here the OP gives the position of the object with respect to motion, that is the position is here. This is the position vector, or you can tell is a radius vector in case of circular motion. Understood all of you? Clear? So again I will repeat, the radius vector is nothing but the vector which shows or which gives the position of the object during a circular motion. Clear all of you? Okay? So it is the vector always drawn from the center. Clear? So here the vector is OP. The vector is OP is your radius vector. OP is your radius vector. Okay, which shows the position of the particle which is mentioned here at P in this case, and OQ where the object is positioned at Q. Similarly. Okay, that means the magnitude of this radius vector always becomes R. Radius R. The magnitude. Listen very carefully. The magnitude. But the position, as the position changes, suppose now first the object is presented P, now it will move to Q. Similarly, so OP is the position vector here, is the radius vector here. Okay, and similarly OQ is the radius vector here. That means it gives the position of the object during the circular motion. Understood? Okay. But with respect to center of the circular motion of the circular path. Clear? This is very important with respect to your center. Okay. So now this radius vector makes an angle del theta in the center. Makes an angle del theta at the center. This angle del theta, what it called? It called angular displacement. It called angular displacement. This is very important. Okay, this is called angular displacement. So during this motion of radius vector, it will make del theta amount of angle at the center. So what is the value of this angular displacement? So del theta is equal to, very simple, the path covered, the arc actually covered at the circumference del S divided by the magnitude of the your radius vector, that is, or the divided by the radius. So del theta is equal to del S divided by R. Del theta is equal to del S divided by R. Okay, so angular displacement, again I will define the angular displacement, listen very carefully. So angular displacement is defined as the angle described by the radius vector at a given time. Again I will repeat, the radius vector is defined as the angular displacement is defined as the angle described by the radius vector at a given time at the center of the circle. Clear? Okay. So angular displacement is nothing but the angle described by the radius vector, okay, at the center during a which type of motion? Circular motion. Clear? Then what is the value of this angular displacement? Now del theta is equal to del S divided by R. Very simple. Clear all of you? So this is the value of your angular displacement. Del S, your del theta is equal to del S by R. So that implies we can simply write the del R value is equal to del theta R. Okay, so this is my angular displacement. First of all, we know about the radius vector. Then second, we know about the angular displacement. Understood? Okay. Okay. Then next a very important physical quantity in a circular motion, that is your angular velocity. Angular velocity, that is your omega. The angular velocity is denoted as omega. Okay, so let us define it. So angular velocity, how we can define it? Now the velocity, the rate of, listen very carefully, the rate of change of angular displacement, the rate of change of angular displacement gives me the angular velocity, because it is a circular motion. So that's why rate of change of angular displacement gives me angular velocity. That means we can simply define omega is equal to del theta divided by del t. Omega is equal to rate of change of angular displacement. So let us compare this with a linear case, straight line motion. Okay, so in straight line motion what happens? There is not any angular velocity, there is a linear velocity in a straight line motion. So what happens there? So the velocity can be defined as a rate of change of displacement, but a linear displacement, listen very carefully, that is linear displacement, okay, in case of straight line motion. So v is equal to ds by dt or del s by del t in case of straight line motion, whereas in case of a circular motion, so angular velocity omega is equal to rate of change of angular displacement. Omega is equal to del theta divided by del t. Very simple. Clear all of you? Okay, so this is your angular velocity. But that is, listen very carefully, but omega is equal to del theta by del t, it is the average angular velocity. Okay, now if we want to find out the instantaneous angular velocity, then what I can write? If I find out the instantaneous angular velocity, instantaneous angular velocity, that means the angular velocity at a particular instant of time. Okay, then how we can define it? Now simply I already know that in case of instantaneous I have to take the limit. Okay, so that is instantaneous, your omega instantaneous is equal to limit del t tends to 0. Okay, so that is del theta divided by del t. So which can be written as in mathematics d theta by dt. Okay, so that is the expression. So omega instantaneous is equal to d theta by dt. Clear? So this is my average angular velocity and this is my expression of your instantaneous. So in whatever the physical quantity, if we want to take the instantaneous value of that physical quantity, then what we can do? Now we must take the limit. Limit del t tends to, here the time period we have to tends to 0, then we can convert it to d theta by dt simply. Understood? All clear? Okay, so this is your angular velocity and this is your instantaneous angular velocity. Understood all of you? Clear? Okay, now so one important physical quantity during, so there are three we have discussed. One is radius vector, okay, one is radius vector, then another one is your angular displacement, then another one is your angular velocity. Clear? Okay, the next very important physical quantity let us discuss in circular motion, that is angular acceleration. That is angular acceleration denoted as alpha. As in a straight line motion there is a linear acceleration denoted as a, and a is nothing but in case of a straight line motion, the linear acceleration can be defined as the rate of change of velocity. But in case of a circular motion, the angular acceleration alpha can be defined as the rate of change of angular velocity. Okay, so that means alpha is equal to, that is del omega divided by del t. Alpha is equal to rate of change of angular velocity gives me the angular acceleration. And remember, this is your average acceleration. This value is your average value. But if we want to calculate the instantaneous value, similarly we have to take the limit. So alpha instantaneous is equal to limit del t tends to 0 del omega by del t. Okay, so simply I can write d omega by dt. Okay, so this is your instantaneous angular acceleration. Clear? So radius vector, angular displacement, angular velocity, then your angular acceleration. Clear? Okay, so that is alpha is equal to d del omega rate of change of angular velocity. This is the average one, and we will, if we want to find out the instantaneous value, we will take the limit only. Del t tends to 0. Understood all of you? Okay, so that is alpha is equal to d omega by dt. Clear? Understood? Okay, so now simply you can also find out the limits. You can also find out the your units, SI units. Very simple. Okay, that is the angular velocity unit is radian per second. The angular velocity unit is radian per second, and the angular acceleration is radian per second square. Listen very carefully. The SI unit of omega, that is radian per second. Okay, and the SI unit of alpha, that is angular acceleration, that is radian per second square. Radian per second is the SI unit of your angular velocity, and the SI unit of your angular acceleration is radian per second square. Clear? All of you clear? Okay, so now so this is all about your the physical quantities relating to circular motion, that is radius vector. Okay, so these are the very important physical quantities relating to circular motion. What are the physical quantities we have discussed? Radius vector, angular displacement, angular velocity. The angular velocity can be average angular velocity, instantaneous angular velocity, then your angular acceleration. It can be also your average angular acceleration and your instantaneous angular acceleration. Clear all of you? Okay. So now, suppose we want to find out another important thing, that is the relationship between linear velocity and angular velocity. Let us find out the relationship between linear velocity and angular velocity. Let us find out the relationship. Derive the relationship. What is the relationship between linear velocity and angular velocity? Clear? So now the linear velocity, how it can be present? We know that the linear velocity v is equal to, if I find out the instantaneous one, listen very carefully. If I want to find out the instantaneous value, then what I can write? Now v is equal to limit del t tends to 0. So del s by del t. So that is your ds by dt. Very simple. The linear velocity is the rate of change of displacement. Understood all of you? Okay. But come to our your circular motion. Come to our circular motion. How the radius vector can be defined simply. Or so what happens now in case of a circular motion, as you have seen in this figure, okay, so we know that the angular displacement del theta is equal to del s divided by r. Del theta is equal to del s divided by r. So that implies I can write del s is equal to r del theta. Del s is equal to r del theta. So now we can put this. Suppose I will take this is equation number 1. This is equation number 2. So I can put this equation number 2 in equation number 1. Listen very carefully. I can put the equation number 2 in equation 1. So by putting equation 2 in equation 1, okay, so what I can get, let us put it. So V is equal to limit del t tends to 0. So in place of del t I can put r del theta divided by del t simply. Okay, so that is equal to, so this r is a constant, I can put it outside. So r limit del t tends to 0 del theta divided by del t. Simply look at the derivation. Okay, so what actually this expression, that is a rate of change of angular displacement. What is it? Now that is that nothing but just we have derived omega, that is angular velocity. Okay, so what the relationship we have got? Now V is equal to omega r. This is a very important relationship where V is the linear velocity, omega is the angular velocity, and r, this r is nothing but your radius vector. Clear? So this is the important relationship between the linear velocity and angular velocity. V is equal to omega r. This is a very important one. Clear? Okay, and this is, listen very carefully, V is equal to omega r. This is a very important relation from derivation point of view and also from your problem point of view. There is a relationship between V is equal to omega r. Clear? Okay. Clear all of you? Okay. So these are the things for in this class. Now we have derived or discussed the different physical quantity about the circular motion. Okay, so now let us summarize something. So the motion of the object, if it is along the circumference of a circle, that type of motion is called your circular motion. Okay, and what are the physical quantities involved there? First, that is your radius vector. Second, angular displacement. Third, angular velocity. Fourth, angular acceleration. Okay, and lastly we have derived the relationship between the angular velocity and the linear velocity. Okay, so this class now as it is, or this remains, and the next class this our discussion continues. Okay, thank you so much.